Hi guys, so this is going to be our little tutorial and overview of CP3 ready for your revision. So CP3 is all about the conservation of energy. Okay, so what we're going to do is we're going to start off by looking at the energy stores. So the energy stores is the potential energy that something has. So that can be found in many different worlds. So this is the potential energy something has. So that can be found in chemical. So that is food, fuel, and batteries. The other thing we've got is kinetic. So kinetic is anything moving. Okay. Another one is elastic. So that's a spring. We've also got electrostatic. So electrostatic is two different charges attracting. We've then got gravitational potential energy. So that is anything at height. So when the roller coaster is at height, it has gravitational potential energy. So this is gravitational potential energy. So at height. Okay. This can also be shortened just to GPE, like so. The other couple we have are down here. We've got thermal. So any hot object. We've got magnetic. And we've got nuclear. So that's otherwise known as radioactive decay. So those are our energy stores. Okay, so we've got chemical, kinetic, elastic, electrostatic, gravitational potential energy, thermal, magnetic, and nuclear. If we keep moving round our sheet then, we've got this bit about a closed system. Okay, so a closed system is when there is no net change to the total energy. So no net change to total energy. That means that there is no transfer outside of the system. So this would be a pan of water. Because there's a lid on it, it is a closed system. So in here, there is no net change between here and the outside. Whereas if we have the pan lid off, we then have a way to have it escape, which means we have an open system. The next section we're going to talk about is our energy transfers. Okay, so that's how our energy is converted between our stores. So that could be done in several different ways. We could have radiation, and that is by waves or electromagnetic spectrum or sound. Okay, so EM stands for the electromagnetic spectrum. Another way that we could do it is mechanically. and that is a force moving through a distance. So a force moving through a distance. Another way to do it would be electrically, which is this one. So that's your electricity going down your wires, so electrical current. And finally, you've got here thermal, or thermally. Okay, so thermally is due to a temperature difference. Okay, so we can transfer by radiation mechanically, electrically, or thermally. So we can get these diagrams like so, which shows our energy stores and transfers in a certain thing. So if we have this as our toy crane, it's powered by battery, which is a chemical store. That chemical store is then transferred electrically to a motor. Okay, so our motor will transfer energy mechanically to get our raised mass. So our raised mass is a store of energy in GPE, because now it is at height, so it's gravitational potential energy. So we've transferred it into a new store of gravitational potential energy. The other thing that we've done is, as we've moved it mechanically, I can't spell anymore, we have produced thermal and sound energy, which means we've got a store of thermal and sound. Okay, so we've now transferred our chemical energy store to a thermal store and a gravitational potential energy store, as we've had a change through our toy crane. Just a point to add about energy transfers is some of the energy will be useful, but some of it will be wasted, and that means it will dissipate, so it will disappear into its environment. So dissipated is a very important word in physics. I would write down a definition if you can. So here, some energy will be useful and some will be wasted and dissipate. Okay, so now we're going to start looking at the thermal energy transfer. So the different energy transfers that we have are conduction, convection, and radiation. So conduction is passed on via vibrations and is best in solids as they are close together. So metals are good conductors because they have their delocalized electrons, which can then move around and bump into the other parts of the structure and pass on the energy. Whereas if we have a fluid, we will have convection. In that we have particles which are dense down here. As they heat apart, they spread and become less dense, and then they cool and become more dense, so they fall. Okay, so heat less dense, rise, cool, and fall as more dense. That is known as a convection current. And then finally, radiation happens in a vacuum. So that's how we get heat from the sun. It is infrared radiation. And it can pass through gases and some solids. So can be gases / some solids. With radiation, if you have dark, dull objects, they will easily absorb and emit infrared, but shiny light surfaces will reflect. So, if we then know that about our thermal energy, we can then apply it to different situations. So if we have walls and we want to stop thermal energy transfers, the rate at which the thermal energy transfers through a wall will depend on three things. So we've got the temperature difference between inside and out, so the temperature difference. We then have the thickness of the wall, and we've got the material. If it's an insulating material, it's going to take longer to pass through. So, a material with a high thermal conductivity is a better conductor of electricity. So, of a high thermal conductivity is a better conductor of energy. Okay. So efficiency of an appliance can be shown using a Sankey diagram. A Sankey diagram is this weird arrow type thing. So over here we have the amount of energy that's going into the system, and then we have arrows coming off showing where it's going to be stored or transferred to. So this is a Sankey diagram for a light. If we have 100 joules of energy going in, we only get 10 joules of light and we get 90 joules of heat. From this, we can work out the efficiency. So if we want to know what the efficiency is, that's how well something works for its job. So efficiency is how well something works for its job, or you can say function. So here we get our light has 10 joules, so we plug it into this equation here. Efficiency equals useful energy over total energy. So our light is our useful thing from a light. So this is a light, Sankey diagram. So down here I've got 10 divided by 100 equals 10% efficient. So lights are not very efficient. We lose a lot of energy to heat. So we call this one over here wasted energy, whereas this is our useful energy. This is what we actually want from our light. So all machines will waste some energy, usually as heat, but unwanted transfers can be reduced by insulation or normally by lubrication. So we'll write that down. All machines will lose or waste some energy as heat. This can be reduced by using insulation or lubrication. Okay, so that is your Sankey diagram. It shows you how useful something is at its job, okay, and how well it is working. So this is a Sankey diagram for a light. Normally it is in proportion as well, so you'd have square boxes to show how much electricity is going in, and then you have to use a key to work out how much energy is here and how much should be here and how much should be here. So it's drawn in proportion to the amount of energy that is in the system and how much energy goes this way and how much energy goes this way. So this time we're talking about gravitational potential energy, or GPE. So GPE is the energy possessed by an object due to its height above the Earth. So this is energy possessed by an object due to its height above the Earth. It depends on three things. So it depends on the mass of the object, it depends on gravity, and it depends on height. Gravity on Earth is always 10, remember. So gravity on Earth is always 10. If you change to a different planet, obviously your gravity changes, so your GPE would change. So we can plug it into a triangle, as it has a equation. So GPE, it goes at the top. We've got mass, we've got gravitational field strength, so I'm going to just put G for gravity, and we've got height. Okay, so what that looks like then is change in GPE is equal to mass times change in gravity times height. Units for that is joules, kilograms, newtons per kilogram, and meters. So on Earth, remember, we've got 10 newtons per kilogram, I should have written. So we then can look at a diagram like this, which is a pendulum. A lot of fairground rides, or swings in fact, work on a pendulum system, and GPE is transferred to kinetic energy in this case. So up here, where the pendulum would be, we would have high GPE. As it moves down here, we have high kinetic energy, so KE. So GPE is transferred to KE on rides, swings, and pendulums. Moving on to kinetic energy. Kinetic energy is the energy stored in moving objects. So energy stored in moving objects. It too has a equation, so it is Ke is equal to half mv squared. So that means we've got Ke at the top, half mv squared. What I mean by m is mass. That is in kilograms. V is velocity or speed, and that is meters per second squared. Ke is in joules, and that is all you need to know about kinetic energy. To have a look at non-renewable energy. So non-renewable energy are our fossil fuels. So they are coal, oil and gas. They are non-renewable because they take years to make. So take when these are burnt, they give off carbon dioxide. So give off CO2 when burnt. That is a greenhouse gas. So greenhouse gas, which is bad for the environment. When I say it's bad for the environment, I mean it is going to cause global warming. What else can we say about these? So they're going to run out eventually because they take so long to make. That means that we can't keep getting them. So they're finite and will run out. So finite means there's a certain amount of them. And because they take millions of years to make, we will run out of them at some point. So, at the moment, our country runs on fossil fuels. We are trying to shift towards renewable resources, but it will take a lot of money and it will take a lot of infrastructure change to be able to go to completely renewable. So they're phasing it in slowly. Another part of non-renewable resources is our nuclear. So nuclear fuels, such as uranium, so we've got uranium, are used to generate electricity. And are also used as energy in spacecraft, so energy for spacecraft. Now the problem is with this is they create radioactive waste, which is highly ionising and it's active for a very long time. So there's no safe way to get rid of the waste. So we've got radioactive waste, active for a long time and very ionising. So there's no safe way to dispose of the waste. And that's our non-renewable resources. Final part to CP3 is renewable resources. So these resources will not run out. So they will not run out, and most do not produce carbon dioxide or pollution. So most do not produce CO2 or pollution. So we're reducing the effects of global warming. Now what we've got is we've got lots of different ways of doing this. We've got hydroelectric, so that generates electricity from water behind a dam. So if this is my water up here, it comes through my dam, it rotates the generator, allowing it to generate electricity, and then the water flows out. So this is generating electricity from water behind dam flowing down a pipe, turning a turbine, generating electricity. Now the next one we have is biomass. Biomass is using animal or plant matter to produce thermal energy, electrical energy, or it can be used to power cars. So this is using plant or animal matter to produce thermal, electrical energy, or power cars. Then we have tidal energy. So tidal energy uses the rise and the fall of the tides, or our tidal currents, to generate electricity. So rise and fall of tide. So tidal is the rise and fall of tide to generate electricity. The next one we've got is solar, and that's converting solar energy straight to electricity. And the last one is wind, so using kinetic energy, so KE, of wind to generate electricity.